In the last lecture, if we have a measure space that is not necessarily complete, then we can form the so-called completion. And this is done by extending the sigma algebra. So that is combining all subsets of mu null sets, and then extending the definition of the measure. Okay, so you will have an extension mu bar, and the resulting measure space will be complete. So we would like to establish an alternative characterization of elements in sigma bar. When can we say that you are in the completion sigma algebra? So for that, we have the following corollary. So this will follow immediately from the previous theorem. So A bar is in the completion sigma algebra if and only if there exists two measurable sets with respect to the sigma algebra sigma, such that A can be squeezed between these two sets and the measure of the difference is 0. So take note that this is somewhat similar to what we have discussed in the previous lectures regarding outer measures, okay, and measurability. Here we have the analogous result in the case of completion measure spaces. So A bar is in a sigma bar if and only if you can squeeze A into two sets, A1 and A2, and this difference A2 minus A1 is A null set. So here, what is A? Of course, is the one given in star. And what is star here? Let us go back with that. This part. So A bar, okay. The A given there is this set A. So let us prove the corollary. Again, we need to establish two directions. Here, let us take simply A1 to be A, and A2 to be the union of A and N. Okay, from a star, we know that A and N is in sigma, therefore A1 and A2 is in sigma. Okay, so it's nice probably to recall here what is star. So A bar is equal to A union B. B is a subset of N. N is a null set. And A and N are in sigma. Okay. So if we take, let's say, the difference between A2 and A1. So what is A2? That is A union N. What is A1? That's A. So this is the same as subtracting A from N. And well, by monotonicity, the measure of n minus a is less than the measure of n, but this is 0. Okay. Hence, the measure of n minus a, which is the same as a2 minus a1, is equal to 0. Note that, of course, by construction, a1 is a subset of a. In fact, they are equal. And a is a subset of a2 because a2 includes the set n. Okay, so that's one direction. Conversely, suppose I have this representation. So if we take, let's say, if I have a1 and a2 in sigma, a1 is a subset of a, and this is a subset of a2, where the measure is difference of the measure is 0. Okay, so we need to, I think they should be corrected. There should be a bar. And so this should be a bar. So this does not make sense. So the one that must be squeezed is a bar. Okay. And is it still true that we have this? Yes. We just need to put a bar in this case. Because a is a subset of a bar, so therefore this is valid. And what? B is a subset of n, therefore A union B is a subset of A union n. Okay, so still we just need to modify or replace A by A bar in the statement. Now we would like to show that A bar is in sigma bar. So to establish this, the same as before, we need to write this as a union of two elements, one in sigma and one in n. And in fact, you can write A bar as A1, and then the difference, the remaining part. So that's A bar minus A1. And this is the case because A1 is a subset of A bar. A1 is being in sigma is already stated here. We need to verify that A bar minus A1 is in n. So it must be a subset of a null set. Okay. However, you can notice immediately that A bar minus A1, since A bar is a subset of A2, so this difference is a subset of A2 minus A1. And and this is what? An element of sigma. Because A2 and A1 is in sigma, and this is a sigma algebra. And so this one is what? a null set, mu null set to be precise. So A bar minus A1 is a subset of a mu null set. And so A bar minus A1 is in N. And that's the proof of the corollary. Okay, so going back to our previous discussions. So given a measure space, one can construct the completion by adding subsets of null sets. However, what we can do is, of course, a measure space is also a pre-measure space. And in that way, you can construct the Caratodori extension. And according to the earlier theorem here, the Caratodori extension of a pre-measure space is complete. So the question is, if I have a measure space, I form the completion. I also form the Caratodori extension. Are they the same? So in some sense, this is some sort of uniqueness of the completion. And in fact, the answer is affirmative if you have a sigma finite measure space. And this will be our next theorem. So let's start with a measure space, sigma finite measure space. Then the Caratodori extension measure space is equal to the completion measure space. So mathematically, or in terms of symbols, you can write this as follows. So the Caratodori extension is X and the set of measurable sets with respect to the outer measure mu induced by this measure mu, okay, which is of course a pre-measure. And the restriction to these measurable sets of mu star, this is equal to the completion measure space, which is X sigma bar mu bar. Okay. So for this, it is enough to show that okay, but what do we mean by equality of three measure spaces? Of course, the corresponding components must be equal. In other words, these two sigma algebras must be equal, and these two measures must be equal. Okay, but then it would be enough to establish the equality of the sigma of the two sigma algebras. So sigma mu star must be the same sigma bar, since mu star restricted to sigma. So a further restriction of this to sigma is the same as mu on your sigma algebra. And this has been shown in the case of the Caratodor extension. So you need to replace the ring by a sigma algebra and the pre-measure by a measure. And by uniqueness of your completion measure that we have established in the previous lecture. Okay, so this is our goal. It is enough to show that the two sigma algebras are the same. Okay, so let's start with the following note. So note that, okay, you can state this as mu being equal to mu star on sigma. And recall that elements of the sigma algebra are all measurable. Okay. Well, in the case of ring, this should be R or even sigma R. But if you have a sigma algebra, then the sigma algebra generated by that collection would be still the same. Okay, so to prove the inclusion, let us take, let's say, let's start with the reverse inclusion. Let us take an A bar in sigma bar. Then from the corollary that we have established a while ago, one can find two sets, okay, A1 and A2 in sigma, such that A1 is contained in A bar is a subset of A2, and the measure of the difference is 0. Okay. So in this case, again, since A minus A1 is a subset of A2 minus A1, and A2 minus A1 is mu star null. Of course, since mu is equal to mu star on sigma, we can replace this by mu star. Okay. We have okay, so A minus A1 is a subset of a mu star null set. Therefore, this must be measurable, okay, by completeness of your Caratodori extension measure space. Okay. Thus, well, the same argument as before. I can write A as A1 union A minus A1. This is in sigma mu star. A1 is in sigma, but sigma is a subset of sigma mu star. Therefore, this is in sigma mu star. Okay. So that's the inclusion a sigma bar subset of sigma mu star. On the other hand, okay, so for the reverse inclusion, so let's start with a measurable set with respect to mu star. And for this, we consider two cases. The first case is that what if the outer measure UPB is finite? Okay. Or let us say the finite case. Or simply write this. Suppose first that the outer measure is finite. Okay. Then we have a theorem last time that if you have a set having finite outer measure, then there exist two sets, let's say A1 in R, but here instead of a ring, we have a sigma algebra, sigma delta sigma delta, but of course, this is the same as sigma, okay? And A2 and sigma sub sigma delta, again, this is equal to sigma, such that A1 is a subset of A, and this is a subset of A2. And of course, the measure of what? A2 minus A1. Well, we said last time that's the outer measure. Is 0. But then, since mu star and mu coincides with an element in sigma, and take note that this is in sigma, okay? Then we now conclude that A is in sigma bar, okay, by the corollary. Because we have what? Squeezed A. So we have two sets, one from inside and one from outside that belong to sigma. Okay. Well, this is the case where if the outer measure B is finite. Now, what if we consider the general case? Or the other case. Suppose that the outer measure of A is infinite. Now, by sigma finiteness, there exists a sequence, let's say xn in sigma such that xn increases to x. Okay, or let's say xn being the union. So the union of the x sub n's is your whole space. And the measure of xn is finite. So this is basically the definition of your sigma finite measure space. So what we do is we take the intersection. Okay. So for each n, A intersection xn is in sigma mu star. Since and why is this the case? Of course, A here is in sigma mu star. What else? Xn is in sigma, and we know that sigma is contained in sigma mu star. And also by what? Monotonicity. So we can take the outer measure of A intersection A. This is less than the outer measure of xn, and this is, of course, just the measure of xn. Here, again, we use the fact that mu is the same as mu star on sigma, and xn is in sigma. And this is finite. Okay. From the above finite case, okay, so what do you mean by this? So if the outer measure of A is finite, we already know that A would be in sigma bar. Since the outer measure of this is finite, we know that A intersection xn is in sigma bar. However, sigma bar is a sigma algebra, so it is closed under countable unions. And if you take the union of this, you get A. In fact, this is, of course, A intersection x, and x is basically the union of the x sub n's. Okay, so that ends the reverse inclusion. So therefore, here we have established that sigma mu star is a subset of sigma bar. And therefore, they're equal according to the previous step. So notice here the application of sigma finiteness. We have what? A theorem a while ago wherein you can what? You can find two sets, A1 and A2, one from the inside and one from the outside of A, having an outer measure 0 for the difference. And in that theorem, recall that we need the condition that our set must have a finite outer measure. So you need to consider the case where your outer measure is finite. And for the general case, you apply a sigma finiteness. So what you do is you take the intersection on these components xn with finite measure, because if you apply monotonicity, you will get that the intersection is finite. And then you just take the union of each components. Okay, so going back to the theorem for a sigma finite measure space, taking the completion measure space, or in other words, by adding subsets of null sets, the measure space will be the same as, or would be the same as extending your measure space using the Caratidori method. Moreover, in the case of Han Kolmogorov measure spaces, the Han Kolmogorov extension, if you complete that, you will get the Caratidori extension. So let me state that theorem. So now let's start with a sigma finite pre-measure space. So you can think of the Lebesgue pre-measure space on the semi-ring of cells. So here we have a semi-ring H. And mu, let's say, be the extension of your pre-measure to the ring generated by H, which is of course again a pre-measure by Han's theorem. Then, if I take this measure space, so this is what the Han-Kolmogorov extension. If we take the completion, this is the same as the Caratidori extension. And take note that we denoted the Caratidori extension in this way. So this is the Caratidori extension. Okay, so therefore, the completion of the Han-Kolmogorov extension is nothing but the Caratidori extension in the case of sigma finite pre-measure spaces. So I will not give the proof of this theorem. You can consult the lecture notes, but the main idea that you wish to establish here is that the outer measure induced by your Han-Kolmogorov extension measure is the same as mu star. So if you want to check the details, please consult the course notes. Okay, so what we would like to see here if we take, let's say, the Lebesgue pre-measure space on the semi-ring of cells, so applying this theorem to that particular example, so we get the following result. So in Rn, you have the Borel or Lebesgue-Borel measure space. Okay, now to distinguish the two uh, measure spaces, we put LB here. So this is your Lebesgue-Borel measure space. If you take the completion of this Lebesgue-Borel measure space, then you end up with the Caratodori extension, which is the Lebesgue measure space. So that's Rn sigma lambda n star, the Lebesgue outer measure, and then the Lebesgue measure lambda n. So again, the completion of the Lebesgue-Borel measure space is the Lebesgue measure space. So in particular, the two sigma algebras involved in these measure spaces are equal. So let us write that down. So this is equal to the completion of the Lebesgue-Borel sigma algebra. And take note that this is what? This is the same as BRN union. Okay, let us write by n lambda n star. So this is according to the previous theorem. You can write the completion you can write the completion sigma algebra as the union of the sigma algebra and subsets of null sets. So here n lambda n star is the set of all subsets having outer measure 0. So this is B subset of Rn such that B is a subset of N. N is Borel. Okay, so in the definition, you can think of this as your so your sigma here is your Borel set. And the measure is 0. So here we need to take lambda n of n is 0. What lambda n? Of course, the Lebesgue-Borel measure. Lebesgue-Borel measure. Okay. So in other words, these are what? Subsets of lambda LB null sets. And in particular, we have the following, that B if you take the outer measure of B, of course, this is less than or equal to the outer measure, Lebesgue outer measure of N by monotonicity. And of course, this is the same as the Lebesgue-Borel measure. And this is 0, so that B is a lambda n star null set. So let us write first that one. So that lambda n star is 0. Hence, B must be Lebesgue measurable. So in other words, B is a null set with respect to the Lebesgue measure, or Lebesgue outer measure. So let us go back to the question at the beginning of this series of lectures. Can we find a connection between Borel sets and Lebesgue measurable sets in Rn? And this question can be answered with respect to this discussion here. Take note that elements of this sigma algebra are basically the Lebesgue measurable sets. These are Borel sets. These are subsets of null sets. Therefore, in particular, there are Lebesgue null sets. So put in another way, this equation here tells us that a Lebesgue measurable set can be written as the union of a Borel set and a Lebesgue null set. So in that way, that's the connection between Borel sets and measurable sets. So you can think of Lebesgue measurable sets as Borel sets except on a null set. So if you think of this as a negligible set, the null set, by negligible, that is, well, loosely speaking, a set having a measure 0, then you can think of Lebesgue measurable sets as Borel sets almost everywhere. And that's the answer to the question that we have posed at the beginning of these lectures. So again, a Borel set or a Lebesgue measurable set is nothing but a Borel set except on a null set. So by removing this null set, you will get a Borel set. And vice versa. If you combine a Borel set with a Lebesgue null set, then you get a Lebesgue measurable set. And this comes from the fact that the completion of the Lebesgue-Borel measure space is nothing but the Lebesgue measure space. And this relies on this general theorem that if you have a sigma finite pre-measure space on a semi-ring, completing the Hahn-Kolmogorov extension would be the same as the Caratudori extension. And that's it for this lecture. See you on the next one.